we? Okay. Right. So good morning, everyone. Today we're going to talk about some number theory, and I've already sent 2 handouts to the WhatsApp group. So for the first 2 hours, we will be talking about p-adic valuation, and in the last 2 hours, we'll talk about a little bit of field theory. So yeah, let's begin. So can everyone see my whiteboard writing clearly? Blackboard, whatever. Okay, nice. So to start off, we're gonna define this function VP, but of course, P is a prime. So VP is a function that, for our purposes, just takes in any positive integer and then gives us a non-negative integer by saying the VP of n is the largest integer k such that p to the power of k is, well, divides n. So basically it's the exponent of p in the prime factorization of n, right? So for example, v2 of 12 is 2, and let's say v3 of 101 is 0, and so on. So a few simple and obvious properties. So first of all, if you multiply 2 numbers, then the VP is just the sum of the individual VPs. Well, because if you multiply 2 numbers, then if you look at the prime factorization, the 2 powers of p will just multiply, and then the powers will just, the exponents will just add, right? So some other things, such as VP of n is 0 if and only if p does not divide n. Right? Yeah, because, well, it's quite obvious. Then VP of n is k. Let's say you want to prove that a VP of some number is k. This is the same thing as proving that p to the k divides n, but p to the k plus 1 does not divide n. Right? And we normally write this as p to the k and then double stroke n. So it's kind of like p to the power of k fully divides n. Well, of course, you have to write it in this notation. You cannot write like 1 double stroke n, then that doesn't make sense. So you have to write it as p to some power and then double stroke n. And that would mean that the VP of n is k. So about this, so you want to prove that n does not, well, it's not divisible by p to the k plus 1, but is divisible by p to the k. So normally for our purposes, you can just take mod p to the k plus 1, because once you simplify n mod p to the k plus 1, if you look at the result, you just have to make sure this result it's not 0 in mod p to the k plus 1, but it's also at the same time divisible by p to the k, then it's sufficient. So you don't have to probably take mod p to the k and then mod p to the k plus 1. You just have to take mod p to the k plus 1. Okay, and something else is this. So if you take the sum of two numbers, if you take the sum of two numbers, a and b, and look at their VP, they must be at least the minimum of those two VPs. Can anyone explain why? HCF. Yeah, kind of. So you basically have a common factor, right? Let's say this one is, let's say this is x, this is y, and let's say without loss of generality, x is the smaller one. Then you know both a and b is divisible by p to the x. So if you add them up, of course, it's divisible by p to the x, right? But an interesting question is, when does equality hold? So is there any simple condition such that you have an equality? Like if it's x and y, and let's say x is a smaller one, I mean the smaller one also can be equal. So what condition forces us to say that this must be equality? Any idea? But it's not a sufficient and necessary condition. It's just a sufficient condition, I should say. So when a equals b, well, when a equals b, okay, yeah, but are they necessarily equal? Like v2 2x is actually v2x plus 1. A or b is not divisible by p. But what if we have like p is 7 and then a is 3, b is 4? Both of them are not divisible by p, but then vp of 7 is 1 more than the minimum, which is 0. Okay, in particular, what if x is strictly less than y? What if x is strictly less than y? So a is divisible by p to the x, b is divisible by p to the y, and then you add those two numbers up. So maybe I could write here a equals p to the x times m, b equals p to the y times m times n. Well, where p has nothing to do with m and n. So the GCD is 1. Now what can we say about a plus b? Well, we can factor a p to the x outside, and then what's left? We have m plus p to the y minus x times n. y is strictly y is strictly more than x. So this number over here, this extra junk over here, is m plus a multiple of p. So that thing cannot be a multiple of p, right? So this is not multiple of p. So that means the VP of A plus B must be exactly x. So a simple condition, and also quite a general condition, right? It's not like just specific cases like the VP of A is 0, VP of B is 1. But it's a very general statement. Of course, it's not fully invertible, as in the converse doesn't really hold, but at least it's quite general. So if VP of A is strictly less than VP of B, then VP A plus B is equals to VP of A. But that doesn't mean that if VP of A plus B is equal to VP of A, then VP must be strictly greater than VP of A. Like for example, I could give you let's say, so converse, let's say P is 7. A is 7 times 1. B is also 7 times 1. Then the VP of A plus B is still 1. But if A is 7 times 1, B is 7 times 6, then the VP of A plus B suddenly is 2. So you cannot really say anything if the VP of A and the VP of B are the same. There are quite a few possibilities. In fact, it can achieve any number greater than the minimum of VP of A and VP of B, if you choose your numbers A and B correctly. Right? Okay. And also, another fact is, well, this has nothing to do with VP, but it will be quite useful in a while. So if we have some number A plus a multiple of P, let's say BP, and I raise it to the nth power. So what if I want to take this thing mod P squared? If this thing mod P, it's easy, right? If it's mod P, it's just A to the n. But what if it's mod P squared? Because the numbers inside here doesn't tell you anything about the number mod P squared. B could be anything. Could be a multiple of P, may not be a multiple of P. But we can somehow take this whole thing and simplify it into something very simple, mod P squared. And how do we do that? Any idea? Binomial expansion and then delete all the powers of P above or equal to 2. Yeah, exactly. So if you expand this using the binomial theorem, you get the first few terms A to the n plus the next term is also easy, n times A to the n minus 1 times BP. But the thing is, the terms afterwards, the exponent of P will keep going larger and larger. And from the next term onwards, they're all P squared and above, right? In fact, I can just ignore everything. remaining, and then just say the remaining terms are divisible by p squared. And hence, if you take mod p squared, you just take these two remaining terms. So it's a to the n plus n times a to the n minus 1 bp mod p squared. Of course, you could do the same thing for mod p cubed. You just take the first three terms, and then you can do mod p to the n in general. Okay. So I guess if you look at your handout, there's a few warm-up examples that you can try. Let me open my handout because I haven't opened it yet. Okay. Yeah, by the way, you can also define a VP for rational numbers, but we will not do that here. It's possible, but then we'll not do that here. We'll just strictly look at positive integers because that's kind of enough for now. Okay, so let's look at the first warm-up problem. So we just do it together because this is not a problem-solving session anyway. So let's say we want to find the VP of n factorial. So how do we? But there's a formula already given in the handout, and I just call you to prove it. So this is just n divided by p floor function plus n divided by p squared floor function, and so on. Well, technically until infinity, because you would stop at some term anyway when the powers of p get larger and larger. At some point, everything else will become 0. So it doesn't hurt to say this sum goes to infinity. So why is this? Why is this true? So what does the first term tell you? What does the first term tell you here? N divided by p and then the floor function. Like if you have, let's say, 101, and then I tell you to divide it by 7, and then take the floor function, then what does this quantity tell you? How many multiples of p below n? Yeah. So how many multiples of p? Well, not more than n. That will be n over p, and then floor function, right? So for example, like if you have v3 of, let's say, 12 factorial, it makes sense to first count how many multiples of 3 there are from 1 to 12, right? Because all the numbers don't matter. All the other numbers that are not multiples of 3, they do not contribute anything at all to this expression. So it makes sense to first count how many multiples of 3 there are, which is 4. So that's why 12 over 3, right? But that's not enough. Why? So why is this not exactly 12 over 3?
Because 9 got the 2 factor 3.
Yeah, exactly. So 9 contributes 2 to the V3, right? So instead of taking 12 over 3, we still have to add those extra contributions by multiples of p squared. Yep, that's absolutely correct. So we just add, but 12 is quite a small number, so so it's might not be very nice because I just need to stop here. So 9, or if I let's say it's 112, right? 112 instead of 12. Then the first term calculates how many multiples of 3 there are. The next term calculates how many multiples of 9 there are, because these numbers, multiples of 9, contribute 2 instead of 1 to V3. So you add them to the previous term, because I mean this term already involved the multiples of 9. You just add one more term to make sure it contributes 2, and then you do again, because you also have the multiples of 27, right? And those numbers contribute 3 to the V3, and hence you add the number of multiples of 27, and then you add the number of multiples of 81, and so on and so on and so on, until you run out of extra contributions, which is when we stop. And that's also when that flow function becomes 0. Yeah. So that's the first formula for the VP of n factorial. So it's quite a fun, probably combinatorial related problem or formula. But there's also a second formula for VP of n, and sometimes it's much easier to use that formula. And that is n minus SPN over p minus 1. Okay. So what's SPN? SPN is the sum of digits of n when written in base p. So assuming you know what base p is, so like what we write here is base 10, right? But if you write it in base 5, it's a completely different expression. You take the sum of those digits, that's SPN. So how do we get that instead? I mean you can just brute force and put it inside. Geometric sum. Yeah, kind of. So I mean, first of all, this formula kind of makes sense, because if these terms on the left, n over p squared, n over p cubed, blah blah blah, if they don't have flow functions outside of them, it is a geometric series that sum up to n over p minus 1, right? And this formula tells us it's a little bit less than that, which makes sense because there's a lot of flow functions here. So first of all, that formula makes sense. Just in case. But now let's try to prove this. So to write n in base p, right? To write n in base p, we say n is equal to a to the m, p to the m, plus a to the m minus 1, p to the m minus 1, and so on, until a naught. So this is n written in base p, and then of course we require that all of the AIs are less than p. So they are digits from 0 to p minus 1. And if that's the case, then what do these terms become? So what's n over p to the k, where k can be any positive integer? So let's kind of write this more nicely. This is p to the, well, first term is pm over pk. And then am minus 1, pm minus 1 over pk, and so on. And let's say k is less than m, right? If k is more than m plus 1, that case is easy. Why? Because this number n must be at most p to the m plus 1, right? If you can see, if you take every single term here as p minus 1, it will be p to the m plus 1. But anyway, let's say at some point we touch the k power term at some point. So in other words, k is less than m plus 1. And then you still have some extra terms, right? You still have some extra terms, and then in the end, we get a naught over p to the k. So this looks okay. It looks a bit more complicated, but remember, these terms are quite small actually. The terms after the kth power. In fact, I claim that the sum of all of these terms are less than 1. And that's also a very easy exercise, because you know what the maximum number those AIs can achieve. It's just p minus 1. So let's write this down concretely. So a to the k minus 1 over p plus a to the k minus 2 over p squared plus blah 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 until a naught over p to the k. Well, this is less than or equal to p minus 1 over, in fact, I'll just bring the p minus 1 outside. P minus 1. And then the remaining terms are 1 over p, 1 over p squared. And can anyone tell me what this geometric series is? Oops, there's a dot 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 here, sorry.
One over p plus 1 over p squared actually is 1 over p minus 1.
1 over, yeah, thank you. So this is, hang on, it's 1 over p minus. Okay, I see what you mean. So if this were an infinite sum, so it goes to infinity, then it will be 1 over p minus 1, right? So in fact, yeah, that would be an easier way to do this instead of writing the exact form of this. So this is less than the infinite sum from 1 over p squared, blah blah blah. And of course, as you said, this is 1 over p minus 1, and hence this is equals to 1. So in fact, yeah, so every single remaining term here in the red box is less than 1. But also at the same time, everything in front of it, they are all integers, right? So this is just an integer plus a number between 0 and 1. So n over pk is also quite easy to find. This is just, okay, but I also have to write this quite complicated. So this is am p to the m minus k. And I hope you see the pattern here. So I'll not write 2 terms. So this is until AK. So now we have this term. And what if we sum it up from k equals 0 to m? Wait, sorry, the k equals 1 to m, because that's what the formula says here, right? So let's see where we can write this. Let's write this here. Let's just change a different color. So the sum of k greater than or equal to 1 of the floor function of n to the p, n over pk. This is the sum of k greater than or equal to 1 am p to the m minus k plus dot 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 plus ak. Okay, this is kind of like a double summation. You can write this as two sums and then you swap the signs appropriately, but let's just not just make our lives easier. We just look at this and write it, and then we just list it out, right? Am to the, let's say if k is 1, then this is like this. I'll just write two terms. And then p to the m minus 2 plus dot 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 plus a1, right? And the next one is k equals 2. For k equals 2, let's just write it here. Am p to the m minus 2 plus dot 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 plus a1. Hang on, sorry, a2 and so on. Okay. Oh wait, hang on. Oh, someone asked, is this 1 over 1 minus p? But it's actually 1 over p. Yeah, okay, nice. So let's come back to this sum and let's see how we can write this out. I think this is not really good. Like let's not write it this way. Let's just write it, because if we do it this way and then we sum up vertically, these sums are also quite weird, because you have am minus 1 and am and then am minus 2 to m. So I think a much better way is to, sorry, I'll just bring this thing over. Oops, no, that's not what I wanted. Sorry. Bring this thing over here. So we remain this alignment of numbers. So it's just the powers of p that are weird here. And of course, a2 it kind of stops one term before a1, but whatever. And then you have these sums. So what if we sum them up? We can sum from the first column, and the first column is am times what? Times the geometric sum from p to the m minus 1 to p to the 0, right? Because this k goes from 1 to m. Remember that. Actually I should also write m here. So what's this? P naught to pm minus 1. And that's probably just pm minus 1 over p minus 1, right? And again, the next term, if you want a spoiler, is also just p to the m minus 1 over p minus 1. And you can probably see where this is going. Now, if you look at the numerator is just, but like, what is this? This plus this ugly, sorry. This plus this plus blah, blah, blah. This constitutes n, right? And then the minus ones, well, this means minus am, and then minus am minus 1, so on. This constitutes minus the sum of digits of n, and then everything you divide by p minus 1. So basically we're done. And let's just end this now and then move on to the next problem. If you have any questions, you can just type it in the chat anytime. Any question actually. So let's look at the next one. So the next one, that one's quite interesting as well. So this is to look at the binomial coefficient of p to the k m over p to the k, where m is not a multiple of p. You want to prove that this number is not a multiple of p. That's quite weird, because if you write down it, the numerator and the denominator of this binomial truth function, whatever, you will see a lot of p's everywhere on top and below. But coincidentally, they all cancel out. So this will become an integer that is not a multiple of p. And in fact, this is also quite an important result to prove a theorem in group theory, which I will not really spoil. But we just focus on this problem. So this thing. Let's look at the VP. Right. But how do we look at the VP of a binomial expression? The thing is, we already know the formula for the VP of a factorial. And a binomial truth function is just a bunch of factorials. So we can just say this is p to the k m factorial minus vp to the pk factorial minus vp to the m minus 1 pk factorial, right? Okay, so how do we compute this? Okay, the term in the middle, that one's quite easy. Anyone can tell me what this is? You can use both formulas above there, but I think the shorter version, the one with the sum of digits, is much easier. So I'll just write down the other two terms first. In fact, yeah, let's just write down everything in the nice font. P K M minus S P P K M minus M minus 1 P K plus S P P K M. Wait, no, S P P K M minus 1. And then over p minus 1. Okay, what's the rate term here? The rate term here is this p to the k minus the sum of digits of p to the k in base p. But what is that? What is that sum? How do we write p to the k in base p? It's just 1 and a bunch of zeros, right? Like p is just 1 0, p squared is 1 0 0, so on. So yeah, the sum of digits is just 1. Yeah, so that's easy. Okay, a lot of things we can cancel here. For example, this term cancels off with this term and this term. And the good thing is, look at the other sum of digits. What is the sum of digits of a number multiplied by a power of p? In base p, if you multiply by a power of p, you just add a bunch of zeros at the back, right? You add a bunch of zeros at the back. Like how if you multiply by 10, you just add a 0 at the back, because we are working in base 10, obviously. But in base p, it's the same thing. So this is just sp to the m, sorry, just sp and then m, and then plus the sum of digits in base p of m minus 1. And then of course a plus 1 here. P minus 1. Okay, but what is this? What is this sum? So again, think in base p. Think in base p. Remember, m is not a multiple of p, right? M is not a multiple of p. So the last digit, the units digit of m in base p is either 1 to p minus 1, right? It's just 1 to p minus 1. So these two terms, m and m minus 1, they just differ at the last digit, right? Only their first digits are different. The tens digit, the hundredth, I mean, I shouldn't call it tens and hundreds. The second digit, the one that represents p, the third digit that represents p squared, all these digits are the same. They just differ in the first digit. But what is the difference of those two last digits? Well, first digit or last digit, depending on you're left-handed or right-handed, I guess. So it's just minus 1, right? And plus 1 over p minus 1. And that's 0. And hence, this is a number that isn't divisible by p. Of course, there are more direct methods, so you could just expand this out and then notice the pattern of cancellation. That's also fine. But I think if you look at VP, it can be much nicer and neater. Okay, so that's that. In fact, let's just skip problem 3 and 4. Those are quite fun problems. Sorry, how do you get the first line? Okay, which line? This line, you mean? Oh, okay. So this is because the definition of NCR or N choose R is n factorial over, well, my blackboard is quite laggy, sorry. R factorial n minus R factorial. So if you take the VP, you just take the VP of the numerator minus the VP of the denominator. Does that make sense? So you just, what's the number on top? The number on top is p to the k times m factorial. What's the number below? Just p to the k and the difference. So m minus 1 p to the k. Yeah, okay. So let's just skip 3 and 4. Those are quite fun problems. You can try it on your own. Now, let's just move on to the next section. And it's a very important section, in fact. So there's something called the lifting the exponent lemma, or LTE, as I will from now on use. So if I say LTE, I mean this lemma. Okay, this lemma concerns this quantity. So the VP of x to the power of n minus y to the power of n. And turns out that it will be a very simple expression if we have suitable conditions for x and y, but those conditions are also quite, it's not very strict. So hang on, I need to charge my PC. So let's look at a few cases, right? Let's look at a few cases. In fact, just two cases. The first case is where p is an odd prime, and then afterwards we look at p equals 2. Okay. So if p is an odd prime, this will be a very simple relation, assuming that x and y are the same mod p, but they are both not multiples of p. So this is the condition we need for this whole lemma to work. And a lot of people forget this, they use LT without remembering the condition. So the condition is p divides x minus y, and p divides neither of x and y. Okay. I mean, the fact that they are both not multiples of y, that one's also quite boring, because if they were multiples of p and the difference is a multiple of p, that means you can probably factor out a power of p before moving on. But yeah, if x and y are the same and they are not multiples of p, the theorem is that this term is just vp x minus y plus vp of n. So very interesting. You just take the exponent and you just chunk it down and take the vp. Okay, and we're going to try to prove this. So first of all, let's look at a few simple cases like n equals 2, right? N equals 2. But p is an odd prime, so we know n equals 2 according to this theorem. If it were true, then this thing would be 0 anyway. But let's just say we want to find vp of x squared minus y squared. What is this? This is vp. Okay, by the way, does this mean x is congruent to y mod p, or is it just x and y separately not 0 mod p? Both of them, both of your statements together. So x is congruent to y, and both x and y are not 0. So yeah, there are actually two conditions here. I just write them in one sentence. Yeah. So let's come back here. So let's say you want to find the VP of x squared minus y squared. And well, first of all, we know that this is just a VP of x minus y plus the VP of x plus y. So nothing special there. It's just factorization. Now, what is this term? Like x and y are multiples. Sorry, x and y are not multiples of p, right? But what's x plus y mod p? X plus y mod p is equals to 2x mod p, right? Because x and y are the same mod p. They are congruent mod p. So x plus y is at 2x. But is 2x a multiple of p? No, because p is a not prime and x is not a multiple of p. So this term here, x plus y, is not a multiple of p at all. So this is 0, right? This is 0. So that's the cool thing about this. If you take mod p and it tells you it's not 0, that means you can directly say it's 0. But if you take mod p and it turns out to be a multiple of p, that means you cannot say anything about VP yet. It could be 1, it could be 2, it could be 3, it could be 4, it could be 5. So you have to choose the right mod. So probably sometimes you have to take mod p squared, sometimes you have to take mod p, sometimes you have to take mod p to something. And if you choose the right mod, you can directly see it's VP. Okay, so So this case is easy. Can we generalize and let's look at all the cases where n is co-prime to p, right? So n is not divisible by p. In which case, we would expect these two to be the same. And let's try to replicate the proof of x squared minus y squared. Just try to generalize it, right? So Vp to the xn minus yn again, use your factorization skills. This is just x minus y plus the junk, right? The things that you get after dividing. And that's x to the n minus 1 plus x to the n minus 2 y. Sorry, the letter y, not asking why. And then so on until y to the n minus 1. Okay, and we expect this thing to cancel to 0. So let's take this thing mod p and then make sure it's not 0 mod p. So what's this thing mod p? Any idea? Well, notice that x and y are congruent mod p, right? X and y are congruent mod p. So the second term is also x to the n minus 1 because it's x to the n minus 2 and times x. And then the third term is also x to the n minus 1 and so on. Every single term here is congruent to x to the n minus 1. And there are n terms. Is that right? Yeah, there are n terms. So this is just congruent to x to the n minus 1. Mod p, remember mod p. So for the case where p does not divide n, we have proven the lemma, right? For the case where p does not divide n, because this thing is not 0, it's not a multiple of p, and hence this whole Vp is 0, and then we are finished for this case. Okay, so that's one case. Now, I claim that we just have to prove, well, for the next case, p equals n. And let's not say why first. You can think about it, but I will prove the case of p equals n first, while you can also think why these two cases are enough to say it's true for all n. But let's just prove this for p to the n first. P equals n. So x to the p minus y to the p. Now, same thing. You have this plus Vp of x to the p minus 1 plus blah plus until y to the p minus 1. Now we expect this Vp now to be 1, right, by the theorem, assuming it's true, which we don't know yet. But we want to head towards that goal. So we know that the appropriate mod to use here is p squared. So we want to take this thing mod p squared. Let's write this in summation forms so it's easier to handle. So this is k equals 0 to p minus 1, x to the p minus 1 minus k, and y to the k. We want to take this thing mod p squared. Now here is where we're going to use that property that we talked about in the beginning of this lecture. So since, wait, why mod p squared? Okay, good question. So we want to prove that this thing has Vp equals to 1, right? Vp equals to 1. That means we want to show that it's not divisible by p squared, but divisible by p, right? If I take mod p, that's fine, but you won't be able to prove that it's not divisible by p squared. In fact, you will just get it's 0 mod p, and then it won't tell you anything about its divisibility by p squared. So if you take p squared, it's much better. It will tell you both things at the same time. So here is where we're going to use that thing, that binomial thing. So let's remain x as x, and y, I will write it as x plus some multiple of p. Let's just say pn to the k. We don't know what n is, but it doesn't matter. Just write it like that. Now, let's just take mod p squared. So what's the second bracket now? The second bracket now is just, sorry, there's only one bracket here. The bracket now is x to the k plus k p n x to the k minus 1. And this is just the sum of x to the p minus 1, which is just p times x to the p minus 1, plus I would just write everything at the same time. So this is just x minus p minus 2, and then the sum of p. Sorry, the sum of k from k equals 0 to p minus 1. Okay. Now, let's just simplify this. This thing, it's quite obvious, right? So this is just p to the p minus 1, p times p minus 1 over 2. Just the usual 1 plus 2 plus 3 thing. Now, why is this not divisible by p squared, but divisible by p? Of course, okay, first of all, it's obviously divisible by p, because both terms have a factor of p inside. Both terms have a factor of p inside. Why is it not divisible by p squared? Okay, this term, I'll just write it like that. Now, remember, I require that p is an odd prime. P is an odd prime. So what does that mean? That means in this fraction, we just have to write this thing as an integer. And then we can take the p outside here, p squared and x to the p minus 2. And then p minus 1 over 2, because that's an integer. So this is a multiple of p squared. We don't have to even look at it now. Mod p squared is just 0. And that's lucky for us, because we kind of introduced this capital N. We didn't know anything about capital N, but luckily that term will just cancel off anyway. So this whole thing is equals to p times x to the p minus 1 mod p squared. But this is not divisible by p squared, because, well, it is divisible by p. It's not divisible by p squared, because x is not divisible by p. And hence, the VP of this is 1. The VP of this is 1. Okay, now it comes back to the question. Does anyone know why we are kind of done now? We don't have to look at larger powers of p or whatever.
Because the larger power of p can use back the same proof of the smaller power of p.
Use back the same. Yeah. I think I get what you mean, and yes, that's correct. Because now look, like let's say you have p squared. Okay, so let's say we have vp to the p cubed m or something. Let's say m is not a multiple of p, and then you get p cubed m. So how does these two cases reach this case? And the answer is, we first have to look at well, we first can look at the case where x is replaced with xp cubed, and then y is replaced with yp cubed. And then you use back the same theorem. Of course, you have to check the conditions first. X to the p cube and y to the p cube are equal mod p. That's obvious if x to y are equal mod p. And then they are both not multiples of p. That's also obvious. So we can use the theorem. And since m is not a multiple of p, this thing is x to the p cubed minus y to the p cubed. Now we have a multiple of p. We just have to reuse the second case. So we just look at this as x p squared to the power of p minus y p squared to the power of p. And by the second case, we know that we can remove the power of p, add 1 at the back, and each time we do it, the powers of p get smaller and smaller, and then we keep adding 1s at the back. So in the end, we can just conclude that it's equal to this. So yeah, this basically covers all of the multiples of p. You can write this more concretely as an induction. Induct on VPN, something like this. Can you show the bottom of the white working? Yeah, sure. But in fact, it's all in the handout already. Okay. So let's look back at the handout. And so we've just proven theorem 1. We've just proven theorem 1. Now, theorem 2 is where you replace the minus with a plus. And I will not repeat the proof. You can try it yourself because it's exactly the same as theorem 1. But of course, we require that n to be an odd positive integer so that we can kind of do the factorization. Remember, x to the n plus y to the n is only factorable when n is an odd number. And if it does, you can just factorize and then do kind of exactly the same thing as what we did here. Okay. So that one's okay. Now, if we're going to look at the p equals 2 case, it's slightly more complicated, but also at the same time, I hope everyone can follow it. So let's just look at theorem 3, right? Theorem 3. In fact, the nice thing, the better way of dealing with LT is to kind of, for the p equals 2 case, is to kind of just derive it every time you want to use it, because it can be quite easy to memorize it wrongly. So theorem 3 is also quite easy to prove. It's the same thing as just now. V2 of x to the odd number n plus or minus, we don't care, is always the same thing as V2 of x plus or minus y. Again, this is a very simple case. You just factorize it and then prove that the other junk is an odd number and hence the V2 is 0. So let's look at theorem 4 instead. That's more important. So theorem 4 is the analogous theorem to theorem 1. So V2 of x to the n minus y to the n, where n now is an even number. Even the powers, you have to kind of separate into cases for p equals 2. So that's why it's not really recommendable to kind of memorize every case. So if this is even, in fact, I never remember whatever's after this. So what I do is I just literally derive it. Like I write n as 2 to the k times m, where m is an odd number, and then y to the 2 to the k m, where m is an odd number. But we know if we are talking about odd powers, we can just remove the odd power. So x to the 2k, 2 to the k, minus y to the 2 to the k. And this thing has a very nice factorization, right? If you factored this before, because you can split it with a minus b, a plus b, but then the a minus b term can be split into like smaller a minus b, a plus b, and so on. So this is just x minus y, x plus y, x squared plus y squared, and then x to the 4 plus y to the 4, and so on. Until the last term is obviously x to the 2 to the k minus 1 plus y to the 2 to the k minus 1. But then v2, we just have to add all of these, right? Now, let's look at these terms. These terms, what is special about them? What is special about them? What can we talk about is v2. Any idea? First of all, they are all multiples of 2. They are all even numbers because we assume x and y are odd. We assume x and y are odd. But what can you say about, let's say, mod 4, for example? What happens when you take this thing mod 4? Any idea? So does anyone know what perfect squares must be under mod 4? Yes, 0 and 1. So if you have a sum of 2 squares and those 2 squares are odd numbers, that means it must be a 1 mod 4 plus 1 mod 4. It must be 2 mod 4. And that means it is not a multiple of 4, but it's a multiple of 2. Hence, the v2 is 1, right? So it's 1, 1, everything here is 1. So v2 is 1, 1, 1, blah, 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 everything here is 1. But how many ones are there? How many ones are there? There are, wait, hang on a second. There are, this is 2 to the 1, 2 to the 1. So there are k minus 1 ones, right? K minus 1 ones. So let's just rewrite this concretely. X minus y, and then plus v2 x plus y plus k minus 1. But what is k? K is just the vp of n, right? Vp of n minus 1. So this is kind of the full form for p equals 2. But you also have to make sure that n is even. You might ask, what if it's a plus? So x to the n plus y to the n. The thing is, we can't do anything about it, because if n is even, that's not factorable. So not much we can do about that. But if it's odd, then this theorem above here covers it anyway. Okay. So yeah, that's LTE for every single case. Well, every single case possible to analyze. Okay, so for the last 20 minutes, let's just try the problems. Wow, it's very laggy. So the first problem, let k be fixed, find all natural numbers n such that 3 to the k is equals to, sorry, it's divisible, sorry, it divides 2 to the n minus 1. So k is fixed, find all n. How do we start to do this? So this is fixed. So that means the answer is probably in terms of k or something. So anyone wants to suggest a first step or something that they observe or something interesting about this problem or anything at all? Because we never know which direction is the correct one. So let's just try to find as many things as we can for the problem. So anyone has anything to say? Yeah, k is greater than 0. V3 2 to the n minus 1 equals k. But is it equals k or something stronger or weaker, depending on what you mean by strong and weak? So this is equivalent to v3 of 2 to the n minus 1. And then what? Equals k or something else? This is just a division property, right? You just want this to divide that. So is it exactly equals to k or it can be something else? It should be larger than or equal to k, right? But for example, it could be 3 to the k plus 1, and so on. So there's also another property that is also I should have put in the front page, but I didn't. So it's like if A divides B, then VP of A should be less than or equal to VP of B. In fact, the converse is true if you include all P. If you include all prime P. So you can probably just write that down or something. Okay, so how do we find this? I mean, how do we like solve this? Anything that we can use? Well, first question, can we use LTE directly? Why or why not? Can we use LTE? because this is kind of like 2 to the n minus 1 to the n, right? So is it allowed to use LTE? Have to make sure they have the same mod, but are they the same mod? 2 and 1? Mod 3? No, right? So 2 and 1 are not the same mod 3. So you cannot directly use it. So first of all, let's just see what kind of n must it be. How can we give a property for n? Yep. So n must be even, right? Why is n even? Okay, thank you. So why is n even? Because if they were even, then you can say, let's say n equals 2m, and then you can say it's 4 to the power of m minus 1, and then you can use LTE because 4 and 1 are the same mod 3. But why must n be even in the first place? Yeah, exactly. Thank you. So 2 is -1 mod 3. And you want this whole thing to be a multiple of 3 because k is more than 0. So n must be even. So yeah, so very straightforward fact. So let's say n is 2m. So I can write it here, since 3 divides 2 to the n minus 1. So n must be even. So let's say n is 2m. So v3 to the 4 to the m minus 1 is equals to, is more than or equal to k. And now what do we do? Now we can apply LTE, right? 4 and 1, they definitely satisfy the conditions required for LTE. So let's just write v3 and then 4 minus 1 plus v3 of m is more than or equal to k. Okay, but what's v3 of 3? v3 of 3 is just 1. So this is just v3 m more than or equal to k minus 1. In fact, these are all if and only if statements, right? So they're all equivalent statements. So we can go backwards. So whatever n that satisfies this last property must satisfy the first property. So what's m? Can we write this in a more layman kind of way? Like, this is too fancy. It's too v3 and blah blah blah. Can you write this in a simpler way, even though they mean the same thing? Anyone? Like what kind of m satisfies this? The v3 of m is more than or equal to k minus 1. Yeah, exactly. So 3 to the k minus 1 divides m. So what's n? Which n must it be? So the answer is just a very short thing, n must be a multiple, or n is a multiple of 2 times 3 to the k minus 1. So any multiple of 2 times 3 to the k minus 1 will satisfy this equation. Or not equation, but relation, whatever. Yeah. Okay. Let's look at another one. If p is a dot prime and a to the n is equal to 1 mod p to the, wait, let me see. Okay, p to the n. Then this implies that a is 1 mod p to the n minus 1. So what can we say first? Like, what does this mean? This means p to the n divides an minus 1, right? But then what can we say about this? Oh wait, hang on. Oops, sorry. I wrote the question wrongly. So, so this is actually a to the p instead. A to the p. Yeah, you might want to correct that. In fact, I will just correct it now. And then send it to the group again. But yeah, so what can we say about this? Anyone? We can write this in VP form, right? Yeah. So VP to the A power P minus 1 is greater than or equal to N. Hang on. It's not responding. Okay, so your VP of A to the P minus N. So the question remains, are we allowed to use LTE? Why or why not? Hang on. I think I didn't send the corrected file. Okay, no, because we don't know if A is 1P. Okay. So you said something very crucial there. We don't know that A equals 1 mod P. But actually, we can say whether A is or not 1 mod P. Yeah, I didn't send the correct file. I will send the correct file later after the break. Well, during the break. We can say what A is mod P. Five squared is 1 mod 2 to the 1. Implies 5 equals 1 mod 2 to the 0. Well, yeah, that's a specific case, but I want to prove the general case. So we want to prove that for all A, P, and N that satisfies the left equation, the right equation is, well, that's true. 5 is 1 mod 1. Any two integers are congruent mod 1. Yeah. No, 5 is, well, 5 is 0 mod 1, but 0 mod 1 is also 1 mod 1. So everything is congruent. Mod doesn't mean you have to be from 0 to n minus 1. Like how 7 and 9, they are congruent mod 2. Or how 101 and 103 are congruent mod 2 also. Congruence is an equivalence relation on the integers. So if I talk about mod 7, then we can also say 49 and 56 are the same. It doesn't have to be from 0 to 6. But of course, if you talk about the remainder, then of course it has to be 0 to 6. But now we're talking about just mod. Okay. We can talk about A mod P, and the answer to that is Fermat's little theorem. So if you take this thing mod P, A to the P is equals to 1 mod P. So let's not take P to the n, but let's take P. By Fermat's little theorem, this is just A, isn't it? So A is 1 mod P, and we are allowed to use LTE. Right? Okay. So yeah, so now we are allowed to use LTE. Vp to the A minus 1 plus Vp to the P, which is 1, is more than or equal to n. Vp to the A minus 1. Wait, how does A to the P equals 1 imply A is 2? Well, Fermat's little theorem says that A to the P minus 1 is always equals to 1 mod P. That's Fermat's little theorem. Kind of has nothing to do with Vp. It's just that this is true by the assumption. This is true by Fermat's little theorem. So A is 1 mod P. Because if A to the P minus 1 is 1, then A to the P is A. This is true for all integers A. Yeah. Okay. So this is Bp A minus 1 is more than or equal to n minus 1. So P to the n minus 1 divides A minus 1, and then yeah, then we're done. That just means A is 1 mod P to the n minus 1. Okay. So all right, now let's look at the next one, which is also quite fun. So 4 times x to the n plus 1 plus 1 is a perfect cube. Is a perfect cube for all integers x. Is a perfect cube for all integers x greater than 0. Wait. Is it for all for all integers n. So the power is variable, and it's true for all powers. So what's x? So prove that x equals 1, or wait, did I say what x? Or I just said find all x. Okay. So find all x.
But even if n is 0, it's also x n plus 1 is a perfect cube, right?
Yeah, but it doesn't really matter anyway. So whether I put this or well, because we just want this condition. Well, that means if I just put greater than 0, it's still fine. We can still solve for x. But if you want, you can just include 0 if you want. So what are the possible values of x? So anyone has any idea how to start? So normally when a problem says, well, this thing is some kind of other thing, perfect cube, whatever, we don't really have to always use the full condition, because perfect cube can mean a lot of things. I mean can have a lot of properties like each VP is a multiple of 3, or there's only one of them between two, but there's none of them between two consecutive perfect cubes, whatever. So you don't have to think, well, you don't have to think holistically. You just have to kind of pick up some small properties that hopefully can attack the problem. Okay, x to the n plus 1 must be even. Yep, that's true, because there's a 4 there and then you want a perfect cube. So whatever x is, x must be odd anyway, right? X must be odd. Okay, so that's a good observation. Good observation. Any other observations? How can we exploit the fact that it's true for all powers n? So if you put n is 1, n is 2, n is 3, n is 4, they all satisfy. For the previous question, why must a to the p be congruent to 1? A to the p is congruent to 1 by assumption. So what we want to prove is that if this were true, whether or not it's true, it doesn't matter, but if this were to be true, then the right hand side will follow. And this left hand side implies that a to the p is 1 mod p, because if it's divisible by p to the n, then it's divisible by p automatically. So basically we can just take any divisor or factor of the modulo and they will still be congruent. Wait, then why do we need the Fermat's theorem part? Because we only know a to the p is 1. We don't know if a is 1. By LTE, we have to examine the condition where a is 1 or not. Yeah, okay, you're welcome. So, okay, back to this problem. How can we use the fact that it's true for all positive integers n? Again, they say this is true for all positive integers n, but normally we just have to use a certain subset of the positive integers n, and then use those numbers to kind of derive a result or contradiction or whatever. So try to narrow down the possibilities. Look at specific examples. Like what can we use here? Look at V2. Yeah, sure, we can look at V2. So that means V2 of x to the n plus 1 must be 3k plus 1, right? Must be a 1 mod 3 number, because there's a 2 to the 2 outside of the bracket. Okay, since this is true for all integers n, let's look at the subset of positive integers where LT is allowed. So we look at the n where LT is allowed. And for the 2 case, unfortunately, only odd numbers work, right? So if n is odd, so basically we just look at the odd numbers n, which we know they're all true. Then V2 x plus 1. In fact, we should write this more carefully. This k depends on n, because if we change n, then this k would change. Okay, so we have this. But v2 of n is 0. I mean, sorry, this is the n odd case, right? We just have to use theorem 3. So this is just equals to 3 to the kn plus 1. Like, okay. So that means it doesn't depend on n after all. But does that help? So that means 3 to the 3k plus 1 divides x plus 1. Sorry, 3k plus 1 on the top divides x plus 1. This is a large amount of numbers. How about we look at some other VPs? Let's look at some other VPs. I think by looking at other VPs, we can eliminate quite a lot of things, quite a lot of x's. So let's let P, which is greater than 2, be prime. So VP must be divisible by 3 for this to be a perfect cube. And then P is not 2, so the 4 doesn't matter. So VP x to the n plus 1. Again, let's look at the n such that LTE is allowed. So for odd n, 3 must divide. Okay, another condition, remember, P must divide x plus 1, right? Hang on. I think I wrote. Okay, you might want to correct something else again. In theorem 2, the condition is not x congruent to y. The condition is x congruent to minus y. X congruent to minus y. Basically, you want x plus y to be a multiple of P. I should correct that also. I will send it in the group later. But yeah, here's the first time we're going to use that theorem. So it's probably a good idea to correct it now. So a condition for this LTE to work is that prime must divide x plus 1. So okay, we're not sure if such a prime exists. Like for example, if x is a power of 2 minus 1, then this prime doesn't exist. But doesn't matter. Let's say it does exist. For odd n, 3 divides VP of x plus 1 plus VP of n. Okay, does this hold for all odd positive integers n? The first term here is fixed, right? The first term here is fixed. But how about VPN? I can remain n to be odd, that's fine, but I can also let VPN be any number I want by choosing the right n. Like I can let n be 3 or 9 or 27 or 81. Those are all consecutive numbers. I mean the VP. I mean sorry, P I can let it be p or p squared or p cubed or p to the 4. This can never hold for all odd numbers n, right? So that's a contradiction. Like put n equals p to the 1, p to the 2, p to the 3. One of these three will already ensure that this relation doesn't hold anymore. Right? So that means x plus 1 cannot have an odd prime factor. If it does, then we just look at that prime factor, right? Vp. So that means x plus 1 does not. I mean, you can just write x plus 1 is just a multiple. It's just a power of 2. It's a power of 2. So again, we eliminated quite a lot of things. But now this analysis doesn't really help much anymore because x plus 1 is. But we already looked at v2. Okay, sorry, that was an old message. We looked at v2 just now, and our result was x plus 1 is a multiple of this power of 2, and k is not even determined, so it doesn't really. It doesn't really tell us much. And our subsequent study found out that x plus 1 is a power of 2. Okay. That means this analysis is not really useful anyway. It's quite useless. So v2 doesn't really help at all. We can prove that it doesn't help because this result subsumes that previous result. So we have to think something else. So not about v2s, but something else. So what is this something else? Let's look back at the problem. X to the n plus 1 times 4 is a perfect cube for all n greater than 0. Let me write this out here so we can keep looking at it. True for all n. Well, notice that if this thing works for x, it should work for any power of x. X squared, x cubed, x to the 4, x to the 5, because if we just change x to some power of x, we're just kind of looking at the same problem with a smaller set of n. But we know it's true for all n. Right? If we look at, let's say, x to the power of 4, then it's the same thing as looking at the original problem where n is a multiple of 4. Does that make sense? So that means not only do we require that x plus 1 is a power of 2, we require all powers of x plus 1 must be a multiple of 2. That's very unlikely, and in fact, we can immediately derive a contradiction from this. X plus 1 is x squared plus 1 multiple of 2. Well, not really useful. I think you can still get some contradiction from this. But I think x cubed plus 1 is a power of 2 would definitely destroy this problem. And why is that? X cubed plus 1 power of 2, x plus 1 power of 2. Any idea? So any powers of x, any power of x works. So x squared plus 1 is the power of 2, x cubed plus 1 is the power of 2, x4 plus 1 is the power of 2, and so on. But why does x cubed plus 1 being a power of 2 would destroy this problem? Can this happen? Like, what's this? This is equal to x plus 1 times what? Times x squared minus x plus 1. X plus 1. But x plus 1 is a power of 2. So this thing is a power of 2. Is that possible? Is this possible to be a power of 2? In fact, is this number even possible to be an even number at all? Yeah, it's not right. X squared minus x is definitely even. Plus 1 is definitely odd. So it cannot be any even number. It cannot be any non-trivial power of 2. This thing can only be 1. Right? This thing must be equal to 2 to the 0. And hence, x is just 0 or 1. But 0 doesn't work, obviously, as you can try. So x equals 1. Yeah, kind of a fun problem. So not just you have to, well, naively apply LTE, which you can do for a lot of cases. You also have to see some generalizations. So if x works, then okay, x cubed also works. So you can repeat that condition for many kinds of numbers. In fact, I think if you use x squared plus 1 to the power of 2, that probably gives a contradiction also. But okay, yeah. So that's one way you can finish the proof. Okay, we still have kind of like 5 minutes left. So well, let's not try 4 or 5. That would take quite some time. I mean, about the same time as the previous problem, but we didn't finish the previous problem in 6 minutes. So let's look at the warm-up questions. Let's look at problem 3, for example, from the warm-up section. So a and b are positive integers where a divides b squared, b cubed divides a to the 4, a to the 5 divides b to the 6. I think you can probably see the pattern. The powers are 1, 2, 3, 4, 5, 6, and so on, and then it's a, b, b, a, b, b, a. So you want to prove that a equals b. You want to prove that a equals b. So what can we do here? How can you translate these conditions into VP or something? So this tells us for any prime p, doesn't matter, for any prime p, VP of A, right? VP of A is less than or equal to 2 VP of B. But okay, there are a lot of AB relations here, like A to the 5 is dividing B to the 6. Then the next one is probably A to the 9 divides B to the 10. Is that right? So in fact, let's just write the most general form for these relations where A is on the left, B is on the right. So it is just 4k plus 1 VPA less than or equal to 4k plus 2 VPB. Does this help? This is true for all k. That's a very crucial condition. So this is true for all positive. Where did k come from? K is just a parametrization of the powers here. So this is like 4. The first one is 4 times 0 plus 1, then 4 times 1 plus 1, 4 times 2 plus 1 is a equals 9. Yeah, the power is 9 case. So I just write every single relation here in terms of some variable k. So I mean, so basically this is true for all. This is true for all k positive, well, non-negative integers. Okay, this is true for all k. What does that mean? So can we say anything from this? This is true for all k. That means if you put k is 10,000 here, it still works. If you put k is 10,000 here, it still works. Sadly, this number here is always slightly greater than VPB, right? It's always ever so slightly greater than VPB. And the larger k is, this difference is small. This difference is smaller, because if k is very, very large, this fraction here, 4k plus 2 over 4k plus 1, is really, really close to 1. So what that means is we can talk about the limit when k goes to infinity. This is just a fancy way of saying when k is really large, then this thing would tend to 1, right? And since VPA, VPB are integers, we can definitely say that at some point, if VPB were to be larger than VPA, this condition would break. This condition would break if VPB is strictly larger than VPA. So taking k to infinity, you can say that VPA is, let's say I'm equal to VPB. Right. In fact, this is true even if we say they are strict. Even if these divisibility relations are strict, that means a to the 5 properly divides b to the 6. That means a to the 5 is not equal to b to the 6. That means this will become a strict equality, right? This will be still true, right? This will be still true. I mean, you have to talk about open sets and closed sets, kind of like topology kind of things. But basically, if k goes to infinity, then this thing goes to 1. And when you talk about limit points, you have to include the boundary points as well. So even if this is strictly less than VPB, if you take k to infinity, VPA is still less than or equal to VPB. Okay, this is for the cases where A is on the left, B is on the right. The cases where B is on the right, A is on the left, is completely similar. Completely similar, except it's like 4k plus 3, 4k plus 4. But nonetheless, you would say similarly VPB is more than VPA for all P. That means VPB and VPA are the same for all P. Every single exponent in the primes of the prime factorization of A and B are all equal. That means A and B must be equal, right? For all primes P. So A is equals to B. Okay, so it's 10 already. So any questions before we end the class? I think I wrote the wrong inequality sign. Where? Oh, yeah, sorry, the blue part, yeah. Okay, this should be also less than or equal to VPA. Okay, thank you. Okay, any other questions or anything else you wanna say or ask or propose or suggest or whatever? Can you explain question 2 last? Which question 2? The warm-up one or the exercises section? The Fermat little theorem. Oh yeah, 是 one in the exercises section. Where is it? So this one you mean? A to the P is 1. A to the 1 is P to the n minus 1. So basically, the last two steps you want to, okay, the last two steps. Well, VP of A minus 1 is greater than or equal to n minus 1. So that means P to the n minus 1 must divide A minus 1. So like which part are you quite, which part? Yeah, over the previous step where the left hand side has minus 1, this one plus 1. You mean this one, you mean? By the way, if you have no questions, you can leave first.
Thank
Well, yeah, welcome, you're welcome. My pleasure. So you mean this blue circle, right? Or you mean, okay, I have no idea which part they're talking about. Or you mean plus 1? The previous step. Oh, you mean this one? Okay, you mean this one? Because we apply LTE. So VP of A to the P minus 1 to the P is just VP of A minus 1 plus VP of P. We apply LTE here. Of course, I skipped a step. I should have written VP P, but that's just one, right? So this is directly from here. You just apply LTE on the left hand side. Okay, you're welcome. So anything else? If not, then I guess I'll see you guys in a few hours. I'm not sure. I think it's 11, probably. Yeah, and then we'll come back and talk about a completely new concept. Okay, then goodbye.